Welcome back, everybody. So I'm wearing my Halloween costume because otherwise I wouldn't get to see you guys on Halloween. I wanted to wish you guys a happy Halloween. Plus I get to use these as pointers now. So when I'm talking about the stuff on the board, I can point to with my little starfish finger. But anyways, so we left off with one more problem to do from 2.6. I'm going to skip talking about the multiplicity trick. It's not super useful. Um, Probably just put that at the end as in the future. I'll just add that as a thing. This one has an interesting case along with the dreaded curly brace. It has, if you notice, it has this 3 minus x term. So that's not the way we typically see it. In every single situation before this one, it was always like 2x minus blah or 2x plus blah or whatever it may be. This is now 3 minus x. So the variable is second and being subtracted. So that does play a role, and we're going to see how that works on this problem. So, but the whole thing, so one thing you could do, and this will bypass that problem, is to just factor out a negative from the beginning. You're more than welcome to do that. You could take this and make this x negative the quantity x minus 3. That will make you bypass this whole situation. However, I don't want to do that on this one because I want to make sure we see what to do if we forget to be that clever on the exam, if this problem were to show up.
You can switch that.
So yeah, you can definitely do this and it makes it fine. However, you have to pay attention to the fact that you've added now a negative out front that is going to play a role. So if you want to do that, that is totally fine. That's you like I am comfortable enough as it is now with dealing with the 3 minus x that I don't need to do that, but it's definitely a good habit if this starts to throw you off on several problems. So instead, we're going to find the VIPs just like normal. Luckily, the thing's already factored for us. So the VIPs are x equals 3, 1/4, and -2. So we have three vertical lines that we need to draw because we have three VIPs. And I forgot to do something. What did I forget to do? Highlight the problematic VIP. -2 is a problematic VIP. And we're doing this for our note-taking purposes, but in the future, like on an exam or on your homework, you don't need to write that it's problematic. You don't need to do that. You can just work with the highlighting. You'll know what that means. Or if you're really good at memorizing without with keeping it on track in your mind, but I can't do that personally. Ben, yes.
Oh, no.
Oh, okay, gotcha. So organizing it -2, then 1/4, and then 3. And we'll pick some test values. X equals -3, x equals 0, x equals 1, and x equals 4. So I want you guys to try and do the first testing value, the segment from -infinity to -2. Now, I recommend writing it in like light pencils because you might make the mistake that I'm hoping that you'll make so that we can talk about it. Making mistakes is part of life. Did you guys get positive? Good, good. Then you're better than me. If you did get positive, then you're better than me because I always got this tripped up because I was thinking about it as x minus 3 instead of 3 minus x. We're plugging in a negative number for x. So it's how did I write this? I wanted to write this specifically. Remember, it's x, it's 3 minus x. So at x equals -3, we have 3 minus -3, which equals +6. So it's going to work differently than we normally see it because we're plugging, like we're subtracting x instead of having x be the first number that we plug in. So that's just something to be aware of. And because that always threw me off. And I'm going to continue it on. So 0, so 3 minus 0, that's positive. 4x, 4 times 0 minus 1, that's negative. But remember, this is an even power. And even powers always make things positive, no matter what is inside. So it's positive in the denominator, numerator, and in the denominator. So it's positive here. That's not a piece that I want. I forgot to highlight that this was a problematic VIP. -2 was problematic. Then we'll try 1, and you've got 3 minus 1. That's positive regardless, and then the other ones are also positive. So that's a total of a net positive. And last but not least, it's a negative, excuse me, times a positive over a positive. And it's because it will be 3 minus 4, which is -1. So that piece is the only piece that's negative, and that is a piece that I want. That is a piece that I want. Any questions on the sign chart? Okay, so you might think that the answer is just bracket 3 to positive infinity. But that wouldn't be completely correct. There's one other thing that's missing. The 1/4. The singleton 1/4 needs to be included. It doesn't matter where you put it. I'm going to put it there. And I'm going to highlight it. Say, needs to be included because x equals 1/4 gives 0 is less than or equal to 0, which is technically true. The quiz is, I forgot to make it, forgot to publish it. That's right. I was going to publish it yesterday, but I got sidetracked. So on the quiz, I'm doing my best to make sure that these dreaded curly brace situations do not occur. But if it does happen on your quiz and you get it wrong, if you forget to include that curly brace thing, it will give you a 0 out of whatever the number of points is. Please let me know and I will correct that for you. I'll give you basically all the points back. I'll give a 0.99 out of 1 or a 0.999 out of 1 just to symbolize that it was technically supposed to be there, but it's kind of a cheap shot. That's a question purely for homework assignments. If there were ever to be one of these on the exam, I would let you know that there will be a singleton value that needs to be included. I'll say it some way, somehow to say like, hey, make sure that you remember there will be a singleton value to include here because that's a niche situation that needs to be taught, like that is hard to do while you're on an exam scenario. So do not fret about this case too much. If it shows up, I will let you know. Okay? Ben, yes.
Is this deep because we have to like work through the entire problem with each other? Doing it by like individual parts.
So like it's an extra added step. One of my students correctly mentioned it, and I think it's a good mentality, is you should always include every critical every VIP when it's a non-strict inequality, except for those that are problematic, because problematic ones can't be included. So with this one, I'm going to include 1/4 because it's a VIP. With this one, I'm going to include, like I already include -3 and 5 by my brackets, but I also need to include 0 because it's a non-strict inequality. That's the like the rule of like the what's done in practice, but it's kind of a like I don't want to make you memorize 80 million different things. I'd rather understand the process and then just go from there. So that's why I don't really like that included the curly brace situation because it does show up on your homework and it's like, ah, darn it. What I'd like you to think of on those situations, if that happens, it's usually like once a blue moon. So if it does happen to you, it's more of a like, hey, I just get free practice doing more of these nonlinear inequalities. So, okay.
That only happens with it's like a greater than or less equal to.
Yes, with the or equal to situations, that's when this will happen. The strict ones, the always the less thans or the greater thans, but not equal tos. Those ones will always be parentheses, every single portion of it. You don't need to worry about any endpoints, any VIPs with non-strict or with strict inequalities.
It's gonna be the wishy blunt. I go.
Yeah, exactly right.
We can go back there. Thank you.
Yes. Any other questions? I feel very silly, but I love it.
But it's still
Starfish hands, yes. I feel like I mean, I'll put it on during the break, but for the people who came in late, happy Halloween. I wouldn't be able to see you guys on Halloween, so I wanted to say happy Halloween. And plus, you only get to wear your costume once a year. That's bull. That's bull. I spent like $70 on this thing. I want to be able to wear it at least once. It's like a wedding dress. All right.
Let's go to conventions.
It's true. I could do that. I could do that. Okay. That is all of 2.6, and that finishes all the material that we need to know for the upcoming exam. The exam is on Tuesday of next week. Your homework assignments for all of Unit 2 have been extended until this coming Monday. So you can definitely get through any of those ones and get some extra credit on those problems, get some anything that you missed that you can add on to it. But yeah, exam review is already posted, and I also sent it out in an email. So please look over that for some extra practice for the exam, and we'll get started with the next bit of material. Any questions on that? Okie dokie. Then we will start unit 1. Like we're starting unit 3, but in order to start unit 3, we need to talk about one thing in addition first, which there's a little bit here that is not super relevant to unit 3, but there is a thing at the very end that is very relevant, which is composition. So first thing we'll talk about is the algebra of functions. If f and g are functions, we can define new operations, f plus g, f minus g, f times g, and f divided by g, which are the sum, difference, product, and quotient functions. So the good news about this, it looks intimidating at first, but all it is exactly what you think it would be. F plus g of x is defined as f of x plus g of x. F minus g of x is exactly what you think it'd be. F of x minus g of x. F times g of x, exactly what you'd think. It's f of x times g of x. And then f divided by g of x, that's f of x divided by g of x. That's what they are. Not surprising, right? It's exactly what you'd think. And that is a good thing. There's certain things later in mathematics, instead of like when you're talking about derivatives in calculus, f times g of x, the derivative of that is not equal to the derivative of f times the derivative of g. That's sadly not true, but it is true here. So these are very, very nice properties. They're exactly what you'd think they would be. Now, because you are combining two functions, the domain gets affected by that fact, because now you're taking two functions into account and you need to make sure that both of them are okay. It was kind of like those situations where we had y equals like the square root of 2x minus 5 over x minus 10, right? There's technically two functions there. There's the top function, the square root function, And then there's the division by x minus 10. There's the 1 over x minus 10 portion. So that is the what's going on here. It's just trying to make sure that both functions are satisfied. However, there's the additional stipulation that g of x can't equal 0, which we already knew about. You can't divide by 0. So even if g of x is a nice defined function, such as just looking at like getting rid of this for a second, x minus 10 is a perfectly fine function. It's defined everywhere. But as soon as you put it into the denominator, now you can't have it equaling 0, which is why we have x can't equal 10. So let's talk about how we find the procedure for finding all this stuff. So suppose f of x is equal to 1 over x and g of x is equal to x squared minus 3x. What you're going to do, if you're asked to find the domain, you're going to find what the function is, but do not simplify. And I'll explain why with another example in just a moment. So just appeal straight to the definition. F plus g of x is defined as f of x plus g of x. That's all it is. No surprise. It's nothing weird. So f of x is 1 over x, g of x is x squared minus 3x. So I'll just replace them with what their equations are. So this is going to be 1 over x plus x squared minus 3x. I'm putting it in parentheses to see that that's what happened. But at the end of the day, I can simplify this and say that this is equal to 1 over x plus x squared minus 3x. And that is your function in its unsimplified form, which is perfectly fine for me, honestly. And if I'm on and if this type of problem shows up on exam 3, I will mention in the problem statement, you do not need to simplify. The main thing that I ask about is if you need to use your equation or thing that you created for something, that's when you need to simplify. But either way, once we've found the function and we haven't simplified it, now we want to look at it holistically to find the domain. So looking at this function again, f plus g of x, we just found it above. It's equal to 1 over x plus x squared minus 3x. Now this x squared minus 3x, does that have any issues? Is there any value of x that I cannot plug into that portion of the function? Of course, every time.
You know,
I just need to buy a new one, but I don't like buying things just because they're not working perfectly. But anyways, are there any values of x that can't be plugged into x squared minus 3x? No, everything works. For the purple portion that I've underlined, you can plug in whatever you want for x squared and you'll always get a number. You can plug in whatever you want for minus 3x and it will always give a number. So that portion has no issues. So that's what I mean by looking at it holistically. We look at each piece and decide whether or not they have problems themselves. The next thing is this portion. And this one, we have an issue if x equals 0. So looking at a number line to visualize this, normally I won't draw it nowadays, but I just want to use the color to illustrate. The function f had the condition that we cannot equal 0. So we have to pluck this one out. But everything else is fair game. So the domain is negative infinity to 0 parenthesis union 0 parenthesis 0 to positive infinity. So that's what I mean by looking at it holistically. Look at each piece. What you'll see in a lot of textbooks is they will talk about the intersection of the two the intersection of these two functions domains. But we haven't really talked about intersections, and what I can tell you is, in my experience, you really don't need to know like besides the union symbol, you don't really need to know too much of set theory until you get into upper division mathematics, until you get into math 251 or above. Set theory then becomes relevant to mathematics, but at that point, you will be ready for that type of abstraction, and so it's not really useful here. So the way the textbook will say this, and if you're looking at Alex, it might even say this, is like the domain, don't write this down. The domain of F is equal to A, the domain of G is equal to B, and that means that the domain of F plus G is equal to A intersect B. So the intersection symbol is an upside down U. And so that's what they'll write, but like we don't have a knowledge of set theory too much. So this doesn't make much sense to us. And I don't want to spend time on it because it's not relevant until you get into Math 251. So instead, my workaround is just to say, look at the function holistically. Look at each piece that was created from the two different functions and make sure that all of those conditions are satisfied. Now, the last step is to simplify as needed. If the problem doesn't say to simplify, you don't need to. Alex may give you that annoying statement of like, you can simplify it more, but you don't need to do that. You don't need to do that unless you have to. There are good, like you don't need to do that. So, say what?
Explain. So it's like 0, origin is 0.
So
So yeah, 0 is the same.
there's an issue if x equals 0. So another way to write that is x can't equal 0. So since x can't equal 0, you need to pluck that out. But the purple one is defined like, other than that, the orange and the purple are defined everywhere except for 0. So that's the reason. Mhm. So then you're going to simplify it as needed. And what that usually means is combining everything so that it looks like a singular entity as needed. So for this function, f plus g, which we saw was 1 over x plus x squared, leave a little bit of space, then write minus 3x. And the fact is, if we want to simplify this into a singular function, we'll need to find a common denominator, which is x in this case. So we'll multiply the first term by x over x and the second term by x over x. Sorry, the third and the second and third terms. And that will give us 1 plus x cubed minus 3x squared divided by x. That equals f plus g of x. Whoa. Yes, China.
Where did you get the x over x?
So great question. I'm doing the x over x because I want these to all have the same common denominator. And x squared right now is x squared over 1, and 3x is over 1. So in order to get a common denominator, I'll need to multiply all of them with a denominator of x. Great question. So if the problem doesn't say that you need to simplify, you don't have to. And if it marks you down on Alex, like on a quiz or an exam, or not on an exam, but if it marks you down on Alex on a quiz for that, let me know and I will give you full credit back. If it doesn't specify that you need to simplify, you don't have to. Okay?
So if it doesn't specify, what do you mean by that? Specify that.
So what it would say, like if it doesn't say in the problem, simplify as much as possible, you don't need to simplify. Or if it said like if it doesn't say simplify your function or simplify your answer, you don't need to simplify.
Okay.
So the question is, I'm going to put both of them up on the board. If you look at the simplified version of the function, you'll find out that we can do this just like we did before when we were trying to find domain back in when we were in unit 1 and say, okay, well, the numerator doesn't cause any problems. The only issue is x can't equal 0. So I get the same result regardless. So why didn't I just simplify at the beginning? And my answer to that is this problem right here. So given that f is equal to 2x minus 6 and g of x is equal to x divided by x squared or x plus 2, let's find the domain of that function. So I want you to make sure you have a like save this whole right-hand side of the graph. All right, save that right half, not of the graph of the sheet, because we're going to need to write a note there. So f divided by g of x. By definition, that is just exactly what you'd think it'd be. It's f of x divided by g of x. That's all it is. Nothing surprising, nothing scary there. It's exactly what you think it would be. So what we do is we rewrite it, and that's going to be f of x, which is 2x minus 6, divided by x over x plus 2. So I don't want to simplify yet, and I'll write why in just a moment. Looking at this thing, if you're looking at it right as it is right now, the numerator, there's no issues. 2x minus 6 can be whatever we want, and it will always be a number. That's okay. But the denominator is a fraction. The big denominator is a fraction. And as such, we cannot plug in -2. Because if we do, then we're going to have, what's it called? If I plug in -2, then this would become -10, and I'd get -10 over the quantity. I'll write this down. Let me instead of just saying it out loud. It's not helpful. So from here, we need x plus 2 to not equal 0. So i.e. x cannot equal -2. And the reason for that, if x equals -2, we get 2 times -2 minus 6 divided by -2 over -2 plus 2, which equals -10 over -2 over 0. But this is undefined. So how can I take -10 and divide it by undefined? Short answer is I cannot. Another explanation to this is, imagine straight from the definition. This, by definition, is this. F divided by g of x is equal to f of x over g of x. If -2 was in the domain of this quotient function, then f divided by g of -2 would have to exist. But if I do this based purely on the definition, don't write this down. We're going to write something else here. So I should write this in a different color. I'll write this in pink. If I try to plug this in, this is f of -2, no issues there. F of -2 exists, but g of -2, this does not exist. That's another way to explain the same thing. If I try and plug in -2 into g of x, it won't exist. Do you have a question?
Yeah, so wouldn't 0 also not be allowed too?
Exactly right. Exactly right. So that's one piece of the puzzle. But the next piece is that from here, since this is the denominator, we can't have it equal to 0. That is, x divided by x plus 2 cannot equal 0. But as we learned with rational functions, the only way for that to equal 0 would be if the numerator equals 0. So this implies that x cannot equal 0. So to recap real quick, before we get to the answer and then we start writing the note. Because that mini fraction is inside the big denominator, we're like, if we like, as long as we're looking at it holistically, we cannot plug in -2 because that would make us have -10 divided by undefined, which doesn't make any sense. Furthermore, because that x over x plus 2 is in the denominator, we can't have it equaling 0. So setting x over x plus 2 equal to 0, the only way that for that to happen is if the numerator equals 0, which is why we get x can't equal 0. So we have x can't equal 2 and we have x can't equal 0. Looking at a number line just to visualize this here, because it came from two different pieces. Here's 0, or sorry, -2. And here's 0. From the blue, -2 needs to be plucked out. And from the green, 0, or from the opposite way. From the green, -2 needs to be plucked out. And from the blue, 0 needs to be plucked out. But everything else is fair game. So the domain of this function is -infinity to -2, union -2 to 0, union 0 to positive infinity. And notice that this question didn't ask me to find f over g of x, so I don't need to even bother simplifying it. I can if I want to, but the question was just asking for the domain, so I'm done when I do this.
So technically you don't have to write it. Yeah, I get to see x plus 2, you can make it a negative income.
Yeah, you could like if you want to like we're explaining it right here in our notes so we see what we did to get to our answer. But on the exam, I mean, I'd like you to say like x can't equal -2, x can't equal 0. I'd like to see that, at least that portion, but I don't need to see like all the we need this to be this way, and the reason for it is this. I just need to see that like, hey, x can't equal -2 and x can't equal 0, so that's where I get my answer.
Okay, so you just want to see that.
Yeah, I don't need to see all the explanations. Connor.
So for the numerator, if you used like the number 3, it'd be 2 times 3, which would be 6. So that'd give it a 0. Would we include that as well or not?
We would, because that's a 0 in the numerator. 0 in the numerator is never the problem.
I'm only, I guess, never mind, because it can't equal 0.
So like, yeah, 0 doesn't work. X equals 0 doesn't work because of the denominator being x divided by x plus 2. If we plug in, so let's visualize, let's see what would happen. If I did 0, I'd get 2 times 0 minus 6 divided by 0 over 0 plus 2. That would be -6 divided by 0, because this right here would be equal to 0. And that's a problem. So the numerator equaling 0, that's not a problem. If I plug in 3, let's see what happens. If I plug in 3, I get 2 times 3 minus 6 divided by 3 over 3 plus 2. That would be 0 divided by 3/5. And 0 divided by any number is just 0. So it exists. It exists at 3. The numerator equaling 0 is never a problem. It's only when 0 is in the denominator that we get undefined or we get indeterminate.
So it's not if the problem equals 0.
Say what?
It's not if like the problem equals 0, it's if the denominator equals 0.
Exactly right. It's that the denominator can't equal 0. Yes. So now that we've finished the problem, I want to talk about this little note on the side. So note, this is the answer to the question above. If we simplified first, we would get f divided by g of x equals, well, we're taking a number, or we're taking a numerator that's just a polynomial, and we're dividing it by a fraction. And what we learn about dividing by fractions, you flip and multiply. So if you want to simplify this and make it look pretty, it would become 2x minus 6 up top times x plus 2, all divided by x, which looks like it's only undefined at x equals 0. So if we look at it by its simplified form and like don't look at the context at all, it's like, oh, there's only one issue at 0. But that's not true. But by definition, f divided by g of -2 is equal to f of -2 divided by g of -2. That's how the algebra works. We defined in the very beginning, the definition of the quotient function here is that it is, you take whatever value you use, usually it's just x as a placeholder until we actually plug in values, but you can plug in any number at the beginning if you want, and by definition, that is f of -2 divided by g of -2. So the thing is, and we wrote this, but now let's write it for realsies. This will equal 2 times -2 minus 6, which is equal to -10. That's no problem. But this, let's use purple. This is equal to -2 divided by 0, which is undefined. And we cannot, as we said before, we cannot plug in, we cannot do -10 divided by undefined. It doesn't make any sense. We can't divide -10 by an undefined value. That itself is undefined. So that's the reason why we don't simplify early. It's because you lose out on a little bit of information based on the original context. The definition plays a big role here. The definition of this function is that it is defined as f divided by g. So when you plug in specific values, you need to make sure that those values work in each function. Any questions on that? So one other thing before we get started on the next one and have a grand old time, you might be wondering why. Why do we even study this? Why is this useful? And in short, it's not super useful. It gives us some fun options, but mainly what it does do, and this is something that I'm interested in as a mathematician, is this means we have a new form of algebra to talk about. So this introduces a cool concept in mathematics that we can create our own algebra systems. Instead of talking just about adding numbers or adding variables, now we can talk about adding and subtracting and multiplying and dividing functions. And that creates a whole new space to study. What happens in this space when you multiply and divide? What happens when you, what other operations exist? What else can be known about this space of things? Mathematicians are really, really obsessed with this. There's a whole field of mathematics called topology, and topology is the study of different spaces and how they look similar to other things. Now, that might seem stupid on its front. It might seem like a really, really useless thing when you're thinking about it. However, it is one of the driving factors that has proven many different things in the real world. Topology basically tries to find out whether or not new spaces that we've created are similar to our 3 space, to where we live and work, right? We live in 3 dimensions. And so if you can create this new space that might have some cool properties, and if you can show that that space is very, very similar to the real world that we live in, now we know more about the real world. That's how it works. That's why mathematics gets money at college, right? We don't actually do anything of real value. We let the physicists do that. We let the physicists figure out how to use it, but we create it and then they use it.
Yeah, they put the logic in.
No, they don't put the logic in. They put the application in.
That's
Different.
Science
Yeah.
is the logic of it. Math
Well,
is the language.
Yeah, math is the language. Yes, that's true. That's the old adage. So this is why I like studying it, is because it introduces to you guys that there is such a thing as creating your own algebras. This is what mathematicians do a lot of times. Like, well, what if I could do this? That's exactly how complex analysis came to be. I've been thinking about it a lot and saying it's a damn shame that we call it an imaginary number I, because it makes it think like we just made it up to have a fun way to talk about it. We didn't make it up. We discovered it. We said, well, what if we could find solutions to things like x squared plus 1 equals 0? What if that did have solutions? What would they look like? And that's when we discovered the I value, saying that we'll make I equal to the square root of -1, and what would that entail? And that created the whole concept of complex numbers. I like the terminology of a complex number more than I like imaginary number, because imaginary makes it seem like we made it up for no reason. So
I thought it was like, if this happens, if some idea.
yes, it's what if this would happen and what do those numbers entail? And they actually show up where you wouldn't think they do. Engineers use them somewhat frequently in upper division engineering. So this is just another example of what we can do with mathematics. So that's why I like this problem. So is it useful? No, but I mean, neither is necessarily writing an essay or knowing that the Declaration of Independence was signed in 1776. It's not super useful to know that exact date. We need to know about the concept, you know, like why we did it. But at the end of the day, are you going to have to pull that out at a party? No.
See those street questions.
True. Yeah. I mean, that situation, but that's just for clout. That's just for trying to get people to get angry for no reason. And I don't subscribe to that. Don't like just trying to make us outrage for the sake of outrage. Okay, so let's go back to it. We've got 3 different functions here. We've got f, g, and h. Find the following functions or values, and if you're finding a function, also determine its domain. So we have f plus g of x. By definition, that is just equal to f of x plus g of x. And f of x is 3x squared plus 21x. And g of x is the square root of x plus 5. And there's not really much simplifying that can be done here. There's not like anything that there's no denominator to get things into a common denominator. There's no way to really write 3x squared plus 21x as a square root without it being completely contrived and unnecessary. So that's as far as we can go. But this question, we found the function, so we also need to find the domain. Is there any issues with the f portion of this function? The 3x squared plus the 21x? Nope. That thing is defined everywhere. So this piece gives no issues. But this piece right here, we need x plus 5 to be greater than or equal to 0. So x needs to be greater than or equal to -5. And if you need to use a number line, go right ahead. But otherwise, you can write the answer to be bracket -5 to positive infinity. And once again, as I said before, so we've looked at it holistically. Now we ask whether or not we can simplify, and the answer is we can. This is as far as it goes. Any questions on that? Connor, do you have a question? Yes.
Why were there no issues on the 3x squared?
The 3x squared? Because it's just a 3x squared. You can plug in whatever you want to the 3x squared, and it always produces a number. 3 times -1 squared is +3. 3 times -2 squared is +12. Any number that you plug into that polynomial portion will always result in a number. It's only the radical portion that causes issues. Is that all right?
Yep.
All right.
It's a positive thing because it was initially a positive number.
Yeah, you need the inside to be positive. Otherwise, like you need those numbers to be larger than -5.
Okay, this is square root of x plus 5. Since it was initially a positive, to be a positive.
That's not how that's not it's coming from the inequality that you've created. So this inequality gives us, if you want to look at a number line, here's -5. That was the only point that was of interest. From the red, or from the green, we need everything to the right of it because we need our x values to be greater than -5. So it doesn't have to do with the fact that it's a positive square root. It has to do with the fact that the inside needs to be positive. Is that what you were asking?
Oh, I
Ben?
guess.
Ben?
That's what I was gonna ask, the inside has to be positive, right? That's why we're setting it at -5.
Exactly right, because we need to make sure that square roots have real values in them. If we were dealing, if this was a complex analysis class, the answer would be everything, because you can, like, even if you get negative numbers on the inside of square roots, those are just complex numbers, and that's okay in a complex analysis situation, but that's not what we're interested in here. So we are like in this course, basically until you get into graduate level mathematics, you don't really care about complex numbers. So
So really, you're just looking at the limits for us, right?
yeah, what's
Say like where you're not including and then where we can go from there.
yes, exactly right. What is the problem and how do we like how do we avoid it? All right. Any other questions, Connor? Yes.
What do we do with H?
With H, we didn't use it in this problem. We're going to use it in the next problem. So it all depends. Sometimes they even give 3 functions and they never actually even mention the third function. Sometimes that happens. But this one, I made sure. So f times h of x, we're finding a function here. So this is by definition, f of x times h of x. And so f of x is 3x squared plus 21x times h of x, which is 5 over x. Before simplifying, because if you simplify this, you might notice that there's a common factor of x inside of f, right? You can factor out an x from f and get x times 3x plus 21. In fact, you can factor out a 3x, and then the x's would cancel. But that would make you lose out on information. Remember, if you cancel a factor, you have to say provided blank does not equal 0. So we're going to look at it holistically right now. We're not going to simplify it yet. The 3x squared plus 21x, there's no issues. Once again, that piece has no issues. You can plug in whatever you want into a polynomial and it will always result in a number. But the 5 over x has an issue. The 5 over x has that x cannot equal 0. So that's our only issue. So on a number line, if you need to draw it, it would look like this. Don't draw it if you don't need it. But 0 has to be plucked out, but everything else is fair game. So that's going to be domain is negative infinity to 0, union 0 to positive infinity. Now that we've found the domain, now if the question asks us, I mean, granted, the question didn't ask us to simplify. So we'll leave it as is. So I should probably add that in, that I want you to simplify it. So I'm not obeying my own rule, but if asked to simplify, then we'd write this as 3x times x plus 7 times 5 over x. And then the x's would cancel because the 3x, that's in a numerator because that's technically 3x over 1. And this x plus 7 is technically over 1. And that x from the 5 over x is in the denominator. Those x's cancel. And we get our final answer, which should be that f times h of x is equal to 15 times x plus 7, which you could also write as 15x plus 105. So if you were asked to simplify, otherwise just leave it unsimplified. There's no need to go any further than that, unless it was asking you additional questions. Maybe it asked you what were the x-intercepts of this function. Then simplify it. If it asks for what the y-intercept is, simplify it. Otherwise, it's kind of not pretty nasty to work with. If it's asking you to find where to graph the function, simplify it. But otherwise, just leave it unsimplified. Any questions? Okay. Let's finish off this example and go from there. And then we'll take our first break. So this question, part C, says find h minus g of -1. So if it's asking me just to find h minus g of -1 and that's it, notice that the next question is not find h minus g of x. The previous two questions didn't ask me to find h minus g of x. So there's no real reason to find that function and simplify it. So what I'm going to say is we don't need to find, we don't have to find, don't need to find, let's say don't need to find the full function h minus g of x because we're just evaluating it. So this by definition, so I'll wait until you've written that down. Wrote that quickly. It's not wrong to find h minus g of x, it's just adding extra work. Because then you have to like plug it in and then you have to write it out and it's all extra work. Extra work that you don't have to do. Instead, you can appeal straight to what the definition of this is. H minus g of the quantity -1 is by definition h of -1 minus g of -1. H of -1 is 5 over -1 minus g of -1. G of -1 would be the square root of -1 plus 5, and that would equal -7. Because you'd have -5 from the first term, and then square root of 4, which is 2, so it's -2, that's why it's -7. So that's why I don't need to find it. I can just appeal straight to the definition. And furthermore, on an exam, you don't even need to write this work. You can just write the answer. You can do these in your calculator or do these in your head, and you're done. So to reiterate though, it is not wrong to find the function first and then plug in -1. It's just extra work that's not needed. Any questions on that? Okay, last one, I'd like you guys to work through that yourselves. Appealing straight to the definition, find the function, look at it holistically to find its domain, and then simplify if needed. If needed. People watching the recording, you should do that too. Okay, so this is what you should get. F divided by G, or sorry, G divided by F of X is by definition G of X over F of X. So that's going to be the square root of X plus 5 over 3x squared plus 21x. Since there's a square root, we need the inside of it to be greater than or equal to 0. So we need to make sure that x is greater than or equal to -5. And then if you look at the denominator, you can't have that equaling 0, because if it did, you'd be dividing by 0. So 3x squared plus 21x not equal to 0, you can factor out a 3x. So you got 3x plus x plus, or times x plus 7 can't equal 0. Which gives you that x cannot equal 0 and it cannot equal -7. So, because of the green requirement, the fact is that we need to be greater than or equal to -5, there's no need to worry about the -7. It's already taken care of. Like, it's basically, you'd get 2 problems instead of just 1 problem. And so it's already there. It's already not it's already a problem. So we don't even need to worry about it. It's like, as long as we make sure that we are greater than or equal to -5, we will never equal -7. So it's not even necessary. But
How is factoring not simplifying?
so I mean that's a gray area, whether or not simplification, like whether or not factoring means simplifying or not. I think it's fine to do either. It's just like, I guess if you're talking about context of just working with a function, simplifying means like just writing it as in simplest terms that you can. You don't need to worry about factoring, but it's not wrong to do so.
Okay, because in the original, -7 would work, wouldn't it?
Nope.
No, it doesn't.
Because if you plug in -7, you will get, like, if you plug in -7, you'll get the square root of -2, which doesn't exist right off the bat, but you'll also get 0. So you have doesn't exist divided by 0. So it's like extrally undefined. It's like it's undefined plus. Does anybody have questions on that? So looking at the number line, I'll wait. Like, if you have a question, please formulate it. But looking at the number line, the green requires us to be to the right, so -7 doesn't even matter. It's not even a point that we need to even worry about because we're already having to require ourselves to be on the green. Yes, Jade.
First glance, is it even necessary to like factor? Because if we just look at the x plus 5 squared, and we just assume that it's not going to be greater than 0 and it cannot be.
So the 0 there has nothing to do with the fact that that the inside of the square root can't be 0. It has purely to do with the fact that the denominator has a factor of 0. That's the reason why it's being excluded. So we do need to factor. Any other questions? Good question. What? Oh, vacuously. That's right. We said that in the break. It is vacuously satisfied. I love this thing. I want to like do a dab with this if I really wanted to and be super cringy. But it would look hilarious. I should. Maybe during the break. When we're not on the recording, when we're not on the record. I don't want that getting out that I do a dab. That would ruin me. Okay. So it is a good time to take our first break now that we finished that problem. Let's come back at 10:42. People watching the recording, go do some sit-ups. All right, we're back and we're going to talk about the difference quotient. This is the main reason why this section we had to wait until now, because this is going to deal with fractions and it's going to deal with, there might be a few situations where we have to do with fractions within fractions, i.e. complex fractions. So I didn't want to introduce this in unit 1 when we didn't know about how to deal with rational expressions. So the difference quotient. Given a function f, the difference quotient is given by, and we're going to abbreviate that dq, not the good type of dq, the dilly bar, right? Dairy Queen, they had the dilly bar. You know what the dilly bar, the circle, like it's the ice cream bar with like dipped in chocolate and it's like in a circle shape. That's called a dilly bar.
I thought you were talking about the fast food place. I'm like, does it not stand for dairy?
Yeah. The DQ stands for Dairy Queen, but their claim to fame originally, not the Blizzard came afterwards, but the original thing was the dilly bar. So is given. I know this is dating me a little bit by that statement, but it is given by, we're going to abbreviate DQ for difference quotient is equal to f of x plus h minus f of x divided by h. So, couple things here, because it's weird at first. But remember, you can plug whatever you want into a function. You can plug whatever you want. You can plug in A, you can plug in triangle for all I care. But a function, you just need to replace x in the function with whatever is inside the parentheses. So we're going to, like, if it has an x squared, we're going to replace that with an x plus h quantity squared, and so on and so forth. We'll see that in a little bit. Now, with regards to these problems, you are not, so the note is you're not done simplifying until the h in the denominator has canceled. You are not finished with these problems until that h in the denominator has been canceled. And I can guarantee you it will always work. You might be wondering, what the heck is this? Why do we care? And in particular, just as a small little observation, maybe you're curious, if a was equal to, let's see here. How do I want to say this? Do you notice that x plus h minus x is equal to just h? So what this actually is, we just simplified it, is that this is f of x plus h minus f of x over x plus h minus x. Don't worry about writing this down. I should have said that earlier. It's a slope. It's, remember, f of x plus h, that's a y value. So it's y sub 2 minus y sub 1 over x sub 2, the value you plug into the function to get that y value, minus x sub 1. It's a slope. And in particular, it's a very, very important slope for calculus. This is the definition of the derivative. So when we do these problems, we're actually computing a derivative. We're just not using the formal language that you use in calculus. But that's the reason why this comes up right now, is we want to prepare you for the algebra that you'll see in calculus. That's the main reason why this is here. So given that f of x equals 2x minus 3, you do not, oh, by the way, you do not need to have the difference quotient memorized. If there's a problem on the exam that requires the difference quotient, I will provide it for you. Calculus won't necessarily, depending on your teacher. If you have like Eric Hutchinson, my colleague Eric, I think he gives the definition. I'm a hard ass. I don't let people have it in calculus, but either way. So you do not need to have it memorized, but it says, given that f of x is equal to 2x minus 3, find the difference quotient and simplify it as much as possible. So the difference quotient, dq, is equal to f of x plus h minus f of x over h. Now, if you are able to compute f of x plus h on the go, kudos to you. You're better than me. I like to calculate them on the side. Now, I'm going to write this in red. John Doe student writes f of x plus h is equal to 2x minus 3 plus h. Why is John Doe wrong? Because he's just silly.
Parentheses.
The parentheses, yes. In particular, the fact of the matter is this right here, this is f of x plus h. Very different. 2x minus 3 plus h, that is f of x plus h after the fact. If I want to do f of the quantity x plus h, the correct way to do this is to replace every instance of x with an x plus h. So this is 2 times the quantity x plus h minus 3. Does everyone see the difference? It breaks my heart when my calculus students make that mistake. Please be better than my calc students. You're replacing x in the function. You're replacing the x with an x plus h. That's what that means. You don't add h after the fact. That would be adding an h outside of the parentheses. So simplifying that a little bit, that's going to be 2x plus 2h minus 3. So plugging that into the difference quotient, now that we know what f of x plus h is, this is equal to 2x plus 2h minus 3 minus 2x minus 3 all over h. Now, this is what John Doe student, once again, silly John Doe, always making mistakes. Let's be fair. Jane Doe did this. She's also silly. She keeps making mistakes. What did she do wrong? God, you said it already. Parentheses. This is being subtracted. The whole expression is being subtracted. F of x is being subtracted. F of x isn't just one term, it's 2 terms. So that minus sign needs to get distributed. And you'll notice if you don't put those minus signs and you forget to distribute the minus, you will get the wrong answer. You won't be able to cancel the h. So we distribute that minus sign, and then we've got 2x plus 2h minus 3 minus 2x plus 3, all divided by h. And look at that. The 2x's cancel. And look at that. The -3 and the +3 cancel. It's almost like that was by design. It is. I promise you, there is, with every single problem we see in this course that requires a difference quotient, there is some algebra that you can do that will allow you to cancel the h. I promise you that. And so when you do that, you've got 2h divided by h, and now the h's cancel, and we have our final answer, which is just 2. And if we had the time, I would explain the graphical implications, but this is basically, as I said, the difference quotient, technically speaking, is a slope. It's the slope of a line. And in particular, it's the slope of the tangent line once you plug in h equals 0.
So Dairy Queen equals 2.
Dairy Queen here is equal to 2. We're all going to Dairy Queen in 2 hours, 3 hours, 2 hours, 3 hours, 3 hours.
You are.
Should all go. Who doesn't want a blizzard, right? I haven't had a blizzard in forever, man. Okay. Next one. Find the difference quotient of this one and simplify as much as possible. I'm going to get it started for us, and then I want you to do the rest. So the difference quotient is dq equals f of x plus h minus f of x divided by h. And off on the side, I'm going to calculate f of x plus h. So that means that I'm going to replace every instance of an x with an x plus h. So instead of 3x squared, it is now 3 times the quantity x plus h squared. Instead of minus x, it is now minus the quantity x plus h plus 1. You should simplify that, then plug it into the formula and cancel as much as possible, and then cancel the h at the end. You're not done until you cancel that h. I would like you guys to go ahead and start working through that now. Same thing goes to you people watching the recording. Okay, so people watching the recording, this is what we get in all of its glory. So f of x plus h, once again, you're plugging in x plus h wherever you see an x. So instead of 3x, it's now 3 of the quantity x plus h squared. Instead of minus x, it's now minus the quantity x plus h. And the plus 1, there's no x's to plug into, so it just stays a plus 1. Then we've got to FOIL this out because it's going to be x plus h times x plus h. And you can do that off on the side. If you'd like, x plus h squared, that's x plus h times x plus h. And so you have to do the distribution thing. First, outer, inner, last. And that's where I've got the 3x squared, the x squared plus 2xh plus x squared. At the same time, I distributed the minus sign into the x plus h, giving me minus x and minus h, and the plus one's just sticking around. Then distributing the 3 into everything, that's where I get the 3x squared plus 6xh plus 3h squared. Now that I've simplified it, I should probably make sure this kind of is not touching it, so we're not thinking it's equal to it. I replace f of x plus h with what it is, which is that long monstrosity here. And then minus f of x, which is 3x squared minus x plus 1. I need to distribute that minus sign in. That's where I get this minus 3x squared, this plus x, and this minus 1. The rest of it was just where it already was. And now we get to cancel things. The 3x squared and the minus 3x squared cancel in blue. The minus x and the plus x will cancel in purple. And then the plus 1 and the minus 1 will cancel in green. So with all of those things canceled, we have a 6xh left over, a 3h squared left over, and a minus h left over. But you'll notice as I've said in the note, you're not done until the h and the denominators cancel. But one thing you may notice is that, like, so you're thinking, how do I cancel it? How do I get rid of it? And the fact of the matter is, oh, here's the fun thing. Not a fun thing. It's a sad thing. Some students will see this and go, oh, I can cancel like that. But you can't. Because in the denominator, h is a factor. In the numerator, it's a term. So you can't cancel terms and factors together. You can only cancel factors vertically and diagonally. So what we might notice, though, is that there is a common factor of h in all three terms in the numerator. So you can factor that out up front. Now 6hx on the inside is just 6x. 3h squared is now 3h. And minus h is now -1. That's when I factored out an h from all of them. The h's cancel, and we're left with our final answer, which is, now that we can call it our final answer because we've canceled the h in blue, and we get our final answer, which is just 6x plus 3h minus 1. A lot of algebra. Any questions on Ben? Yes.
Yeah, two questions.
Sure.
I don't know how to ask it, but in the f of x plus h equals the rest, right? Why are we substituting in?
Here?
Yeah, at the very beginning. Why are we substituting in the f of x equals 3x squared? For x plus h and not just the x part of the x plus h? Like, we're doing it the other way around, whereas the f of x, we're putting the term we're given into it.
So, like, why are we doing this off on the side and then subtracting it here?
Yeah, why are we substituting the x and the three and the f of x equals part? Why are we substituting in x plus h for our x values up there?
For here?
No, on the right.
On the right.
Yeah, we're getting rid of the x's.
We're
And
getting
we're adding x plus h. Why are we not doing it the other way around?
Trying to think of. I'm not sure I'm understanding the question yet.
I guess this is why you're plugging in
X.
X plus H, and then you're doing it again after the fact. That's what I was thinking when I first did it. I just got to the first step,
Mm-hmm.
and then the second step, I was just like, what? Why are we plugging in the 3x plus H again? No,
What?
I got that,
Why are we doing this?
yeah.
So, okay. So what I'm doing on this purple section is I'm computing this off on the side. What I'm doing is I'm just trying to take care of it so I don't have to do it all at once. To show you very, very quickly, it's going to be chicken scratch, but this is why I avoid it. So if I want to go from here immediately to plugging it in, then I have to do 3 times x plus h squared minus x plus h plus 1. Is it plus 1? Plus 1 minus parentheses 3x squared minus x plus 1. And for me, that ends up being a little more algebra than I'm comfortable with doing all at once. So I like to do this calculation off on the side so that I don't have to do it all while I'm still trying to simplify at the same time. Is that your question then?
Kind of. You put 3 times x plus h squared. Why
Yeah.
are we not putting the original thing that we did on the right in place of the x and then adding the h after?
Excellent question. So why? Okay. So the reason for that is that we need to know the distinction between f of the quantity x plus h versus f of x quantity then plus h. These are two separate quantities. One of them, the first one, is saying take the function and input the value x plus h. That's what this is doing. This is saying take the function f and replace all of your x's with an x plus h. Whereas this one is saying compute f of x and then add h. See the difference? So like the key example, like let's look at a like if f of x is equal to 2x plus 1, then f of x plus h is 2 times x plus h plus 1, which is 2x plus 2h plus 1, whereas this would be 2x plus 1 plus h. They're not the same. So they are two different things. Because one of them is happening before you input it into the function, and one of them is happening after you input it into the function.
Yeah, and that makes sense, but why not, if that f of x on the bottom is the same x as the one in the x plus h,
Mm-hmm.
why aren't we putting it in the parentheses with b plus h to compute it all together?
I'm sorry, I'm still having trouble understanding the
I guess
question.
my confusion is every time we've been given a value for x, right?
Mm-hmm.
Plugged it into the formula we had. Why are we working in reverse now? We're plugging in the formula into the value of that.
So, okay, I think I understand. So the thing that we need to really work with here is this is a weird concept, absolutely, because instead of like the function is defined fx, and now we're replacing the x with an x plus h. Don't think of it as the same variable, really. Like imagine a function f of box is equal to 3 times the box squared minus the box plus 1. So what I'm doing is I'm putting inside the box x plus h. Maybe that helps. Does that help it make?
Yes.
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 So imagine what a function is it's just put in a box and then input it into the function, input it inside it. So in particular, in this context, I'm putting an x plus h into the box. Is that all right?
Yeah.
Great questions. This is very, very important because this is a killer for some of my calc students. So I'm glad we're talking about it now. Any other questions? Oh, yes, yes. Any other ones?
Oh, I did have a second question. I
Mhm.
remembered. You said that h is, in the very bottom, 6x plus 3h squared minus h, you said that's a value. Right?
Each one of those is a term.
It's a term, right? And we need a value, right?
Uh,
Or a factor. or
we need a
whatever.
factor,
We need a
yes.
Factor. Okay, so -1h, wouldn't that make it a factor? That's why we pulled out the h?
So yes, but it needs to be a factor of the whole thing. Once I have factored it out, now it is h times this quantity, making it the factor that we need so we can cancel it.
Okay.
Before then, it's just a term. Another way to think about this, maybe this helps. I'm dividing. What you can think about it instead is 6xh divided by h plus 3h squared divided by h minus h divided by h. Because when you're dividing by a monomial like h, that's just dividing each thing by h.
Gotcha.
So that's another way to think about the same problem. It's just this usually ends up taking less time to write instead of having to write it like this. But it's still valid to do that. All right. Now we go on to the make or break one, as it were. So g of x is equal to 16 over x plus 9. And we want to find the difference quotient and simplify as much as possible. So I'll get us started and then I'll have you guys finish it. So dq, oh no, it's not f. It's fine. The name of the function is irrelevant. So this is g of x plus h minus g of x all divided by h. So off on the side, I'm going to compute g of x plus h, just so that I don't have to do it all at once, while I'm also working with other things. So, and if it helps you, definitely do the box thing. The box thing helped me when I was a student. So if you prefer, first write it as g of a box, which would be 16 over box plus 9. And then put the x plus h here. And that will help you out. If that helps, please do it. It's not wrong to do that. It's and if any teacher gives you flack for that, please let me know. And I will once again I'll defend your honor. I'll bust out my my katana that I asked for when I was in 6th grade. I My parents still have it somewhere. Or my mom, rather. So I need it, Moff. You're gonna kill a student? No, no, no. I'm to defend us. I'm gonna kill another instructor. Oh, that's better, son. That's better.
You're saying this would record.
I know. I would never do that. Just mortally wound them. It's different. Well, not mortally wound them.
Can just flip it.
Yeah, I'll just bust that out. Poke him in the eye with this little poker. So x plus h, plugging that in, replaces the x with an x plus h. So we have 16 over x plus h plus 9. So going back to the difference quotient, this is now 16 divided by x plus h plus 9 minus 16 over x plus 9, all divided by h. And I'm going to do and make this look obnoxious for a second to remind us about this is a complex fraction, right? It's got fractions within fractions. So we need, oh yes, Jade.
Need to interrupt, but
No, it's all right.
I thought we needed like the parentheses.
I guess you can, yes. It will be like this first, but luckily there's nothing being multiplied into it or anything like that. If this had been like a 3x plus 9, that's when I definitely want to have parentheses. But because it's a 1x, it doesn't do too much. But it's not wrong to do so. It's probably more correct. And then that's 16 over x plus h plus 9. Totally valid point. So this is a complex fraction. And so one way to do it would be to just find a common denominator in the big numerator. That's fine to do. Or we can use our trick that we learned with complex fractions, which would be to multiply across this main bar by the LCD, which in this case would be only x plus h plus 9 times x plus 9. I forgot to make that in red. I meant to make that in red. And we don't remember, we have to do this to both the numerator and the denominator. I wish my calculus students did it this way. I usually have to do it the old-fashioned way, and it takes a lot longer. This will be faster, as you'll see in just a moment. So I'm doing the complex fraction method that we learned, which is to distribute it now, to multiply the main fraction line. That's why I've highlighted it in, with a thick blue line, and I'm multiplying across that line. So in the big numerator, this gets distributed. And then in the big denominator, it just gets multiplied together because there's no fractions really to do. There's no fractions to distribute. There's only one term. There's no need to distribute. It just multiplies all together. So this becomes 16 times x plus 9 minus 16 times x plus h plus 9, all divided by h times x plus 9, x plus h plus 9 times x plus 9. And make sure you're on track with that. Take a second to deduce it for yourself. Make sure you understand where everything came from. I'll explain in just a moment, but I want you to try and fill in the gaps in the algebra yourself.
Show when you do it like individually on the numerator. You know what I mean?
Oh yeah, I can do that while we're yes, I can do that. Just a moment. Okay, so what's happening is that when I distribute this red piece into the first term, the x plus h plus 9s cancel, so I just have a 16 and an x plus 9. Then when I distribute it into the second term of the big numerator, the x plus 9s will cancel, leaving me with just a 16 and an x plus h plus 9. And then the denominator, there's nothing to cancel. It just becomes h times this quantity. And now we'll take care of some algebra. We'll distribute that 16 in. We've got 16x plus, what's 9 times 16? 144. 144 minus 16x minus 16h minus 144, all divided by h times x plus h plus 9 times x plus 9. And I'd like you to start working through simplification. One of our students has asked me to show the alternative method, so I'm going to do that off on the side while you guys are working through the simplification. A lot of x plus 9s. Okay. So you should get, at the end of the day, negative 16 over x plus h plus 9 times x plus 9. Because once you distribute the negative 16s as we did, the 16x's will cancel, the 144's will cancel, and all you'll be left with is a negative 16h over h times x plus h plus 9 times x plus 9. The h's cancel. That tells us that we're done. Once the h in the denominator gets canceled, you're all finished. And you get your final answer, which is right there. And then what I've done on the side is I've done it by the alternative method where you find a common denominator in the big numerator. And if there was one in the denominator, you also find it in the big denominator. So you multiply what they're missing. And then you get this expression divided by h. And the fact is h over 1. So you can think of that as flipping and multiplying by 1 over h. That's why it becomes this. And then the h is canceled just like before, and you get to the same result. It just ends up looking more complicated in my experience, and a little more room for ambiguity and also mistakes. But that's another option to do. Any questions on that? Okie dokie. And yeah, of course, if you'd like to take a picture of the alternative method, please do so. Then there's this challenge problem. I encourage you to do it. I have a hint here, and it's to multiply by the conjugate. And the reason for that, the key fact that you need to know is that if you have a plus b and you a minus b, it doesn't matter which one comes first, but if you have a minus b times a plus b, that becomes a squared minus b squared. Now, that might seem like gibberish right now, but definitely try it. Just write the first step of cleverly multiplying your difference quotient by that quantity, which is the conjugate of what you'll find, and you will be able to cancel out the radicals.
How do you do it now?
Yeah, you can verify that by foiling. If you do this multiplication, you'll get an a squared, then you'll get a positive ab minus an ab, and then minus a b squared. So the ab's cancel. So feel free to try that this weekend. Great bonding experience with you and your significant others, which you all have, because you definitely tried my second date technique of getting the polynomial thing, right? Has anybody actually done it yet? I need data. I need the data. So we'll move on to the next topic, the one that's going to be most important for Unit 3.1, which is composite functions. Yes.
Or that data 16,
Uh-huh.
for the numerator, then you just flip and cancel the x plus 9.
Flip and cancel the x plus 9.
Like complete, like if you take out the x plus 9.
From here?
No, that's,
From here?
yeah.
So they're on the same level, so they can't be canceled. They can only multiply together.
No, well, you know how we're working with like fraction over fraction type of thing?
Mhm.
We couldn't do that with that?
No, because there's no more mini fractions. There's no more mini fractions. So if this,
I'm thinking, that over 1 on both. Says we're multiplying.
right here,
Yeah.
like
I'm
that.
not thinking about the negative 16, I'm just thinking about the x plus h plus 9
Mm-hmm.
and the x plus 9.
Putting them over 1.
Yeah,
Well, then if we were to do that, then we'd be flipping and multiplying by that, but that would just bring us back to where we started.
I was just thinking we could get to h again.
No, unfortunately, we're done here. We can't do any more algebra. I know we all want to do more algebra. I do too. I want to do as much algebra as possible, but unfortunately, that's where we stop. Unfortunately. So, one of the most useful things in later mathematics is composite functions. If you plan on taking Math 251, you will deal with composite functions for the rest of your life. If you plan on being a math major, composite functions are everywhere. They're in abstract algebra, they're in algebraic geometry, algebraic topology, complex analysis, real analysis, ergodic. Anything will involve composite functions because they are so common. Given functions f and g, the composite function sometimes called the composition function. Either way is fine. Composite function, composition. It's given by this. F circle g of x. It looks like fog. It's not a multiplication symbol. It's not a dot. It's an open circle. It's an open circle. It's different than the product function. F times g of x. Different. F times g of x, which is usually abbreviated fg of x. That is a solid little tiny dot, whereas this is an open circle. That's what composition is defined by, or is denoted by. And what this is equal to f of the quantity g of x. And you say f composed with g.
Let's see.
Where do I use my jargon? Yeah, okay. I brought that in the next bullet point below. But that's how it's said is f composed with g, and it's equal to f of the quantity g of x. So you're plugging in a function into another function. Meta, very meta. You're functioning a function, essentially. And there are very, very many implications of this concept. We don't talk about function mappings in this class because it's not really relevant for this course, but that's what a lot of upper division mathematics is all about. It's about composing functions to create something on a new space. So these show up everywhere in mathematics, and there's a rule in calculus called the chain rule, which deals with composition. They should really call it the composition rule, but I know why they call it the chain rule. But either way. So the note is that order matters. F composed of g of x is f of g of x. And g composed of f of x is a terrible quarterback who should never have been on the Rams. I hate him. Jared Goff. Hated him. He was the bane of the Seahawks' existence, and I know we all feel that way. I did not like that he was on the... He's a mediocre quarterback who just had a good coach. So, anyways, Goff. This is g of f of x by definition. These are not rarely equal. So we've just learned another operation that we can do that is not commutative. The only so this is very, very important in mathematics. Not all operations are commutative. In fact, most operations in mathematics are not commutative. The only ones that are really, really common that are commutative are multiplication and addition. But this is just another example of why operations aren't necessarily why commutativity is such a big deal. It's a rare property, and it's important when you have it. It's super useful because it means you can compute things any way you want them. Whereas this shows us that you can't always do that, especially with composition. So, given that f of x is equal to x squared plus 1 and g of x is x minus 3, find the following. F composed of g of x. Now, as a small note, because I'm going to be using this terminology a lot, f equals the quote-unquote outside function here. And g, in this case, is the inside. Because it's further in, it's inside of, it makes sense when you look at this. G is the function on the inside, f is the function on the outside. That is a very useful way to think about this, and it helps us a lot in intuition and how to work with it. So in the next case, with g composed of f of 2, this time f is the inner function, g is the outer function. So whatever function is closer to the input x or whatever it may be, that's the inner function. So let's compute f of g of x, and then we'll take our break. So this is, by definition, f of g of x. And so I will replace g of x with what it is. So this is equal to f of the quantity x minus 3. And if you think about that box concept, you're putting inside the box, you're putting in x minus 3. So we're replacing every instance of x in f with an x minus 3. That's going to be equal to the quantity x minus 3 squared plus 1. I know it seems super random at this moment. Like, this seems like such a random idea, and I wish we had time to talk about the nuance of it and why it's useful, but it is something that shows up. I promise you it will show up in your future. If you plan on taking multiple math courses, if you plan on taking calculus, you'll see it there. If you plan on taking Calc 2, you'll see it there because of the chain rule. Calc 3, you'll still see it there because of the chain rule. Math 2, 251 linear discrete mathematics, you'll see it there when you talk about function mappings. In linear algebra, you'll see it, but they won't talk about it. It's there, but it's not really there. So you'll see it everywhere. It's in every math course from here on out. So there's a reason to study it. So once again, you're putting g inside the function. Imagine putting g in the box. And so simplifying that a little bit, that'll be x squared minus 6x plus 9 plus that 1. And that's equal to x squared minus 6x plus 10. We're going to take a break. Let's come back at 11:42, and we will continue on with this concept. People should recording to do some guided meditation and some squats. I don't know. All right. So we've got a couple more things to do with composition functions. So g of f of 2. much like that previous example where we're not actually tasked with finding g of f of x or g composed of f of x. We don't need to find it. And so I'm going to write this. We don't need to find g composed of f of x to find this. We can appeal we can use the definition. So what I mean by that is, by definition, I'll let you write that down before I go faster. We don't need to actually compute g of fx. As you can see, it kind of takes a little more time. The f plus g and the f minus g and the f times g, it doesn't take too long to compute, but these ones, especially certain ones, can become quite tedious to do. So instead, you can appeal straight to the definition. G composed with f of 2 is by definition g of f of 2. So what is f of 2? F of 2 is going to be 2 squared plus 1, which is 5. So this is instead, we computed what f of 2 was, it's 5. So instead of g of f of 2, I can write what this is. This is equal to g of 5. And so then I just plug it into the formula for g, and I'm all good. That would be 5 minus 3, which is equal to 2. So far faster. I encourage you, if you're bored, try and compute g composed of f of 2. G composed of f of x, and then plug in 2 and see which one's faster. Especially if you don't have to write what we wrote. It took longer, but that's only because we were explaining the concept. Then, the last one, unless there's any questions on that.
Yeah,
Yes.
so the 2 is just gonna be in place of the x or the f function.
For the g function. Oh, yeah, for the f function, yes.
Okay, and then we're just plugging that into the g function afterwards.
Yes.
Okay.
So it's this systematic thing. First, we plug it into g, or for in this case, first we plug it into f, then we get that result, then we plug that into g. All right. The next one, f composed of f. Nobody told me I couldn't compose a function with itself, and so I can. So f composed of f of x, that is just f of x. So that's going to be f of x, which is x squared plus 1 from us. So this is f of the quantity x squared plus 1. So I'm going to replace every instance of x in f with itself, with x squared plus 1. So it's very meta, but it's going to be equal to the quantity x squared plus 1 squared plus 1. If it helps you visualize it, remember that f of a box, let me make it a rectangle more specifically. F of a rectangle is the rectangle squared plus 1. And we're just putting x squared plus 1 into that rectangle. I guess no, box means any type of rectangle. Square is a square.
Is it like, how I'm thinking about it, it's
Mhm.
like, on a game, you got the first level, X, plug it in, you take the result, go to the next one.
Yes. Exactly. It's going down this rabbit hole, going down each level. And so that actually brings up a very, very fun point, is in mathematics, I've had to do it in the past where I've had to do f composed with g, composed with h, composed with k. So I have to compose multiple functions, and it just works in the opposite order. So if you have this, first you plug it into k of x, then you plug that result into h of x, then you plug that result into g, then you plug that result into f. So it works inside to the out. You work inside out. You work backwards. Well, backwards, but it's inside function to the outer function. So in fact, one of my functions, like we had to define Fn of x to mean f composed with f composed with f composed with f n times. And so we do that all the time in mathematics just because we're bored. Um, honestly, that's really what it is. But anyway, so we can leave it like that. If it doesn't ask us to simplify, we don't have to. We can leave it like that and it's all good. Alex might throw a hissy fit and say you should simplify it more, but unless it says, you can just look at it and say you didn't ask me to simplify. So this becomes, if we do want to simplify, x to the fourth plus 2x squared plus 1, and then plus that 1 on the outside, which gives us x to the fourth plus 2x squared plus 2. Okay. Now, much like I want to, once we finish writing this, I want to go back to that one case where we're talking about simplification, whether we should do it first or second, because there's an important concept there that plays a role in this situation, because we're about to talk about how to find the domain of a composition function. So going back for a second and looking at this problem again, the definition played a very, very big role. We couldn't plug in -2 even into the simplified version because if you're appealing straight to the definition, you have to be able to plug it into f and into g. And it wasn't able to be plugged into g. So that's the thing I want us to keep in mind. In order for it to be part of the domain, it needs to be able to be plugged into both functions. So when it comes to composition and how to find the domain. So let's look at this problem. F of x is equal to 1 over x squared minus 8 and g of x is equal to the square root of x plus 3. Find f composed of g of x and its domain. So step 1, before you even begin, find where the step 1 is to find where the inside function is undefined. So looking at f composed of g, fog of x as it looks like, that is going to be f of g of x by definition. So this is the inside function. And it's g of x equals the square root of x plus 3. The inner function is x plus square root of x plus 3. The domain of that function is all numbers greater than or equal to, so we need x plus 3 to be greater than or equal to 0, which means we need x greater than or equal to -3. I'll explain why once we get to the end. You'll see there's a question at the no, I didn't put the question. Yeah. I have a question down there that will answer why we have to do step 1. So suspend disbelief for just a moment and just say that you need to make sure that to find out where the inside function is undefined. Then you will find the composition function and simplify it. So f of g of x, that is f of the square root of x plus 3. That is the function g. The inside of f right now is g of x. That's what g of x is. So now every instance of x inside of f will be replaced with the square root of x plus 3. So this is equal to 1 divided by the square root of x plus 3 quantity squared minus 8. And then here, the square root and the square will cancel and leave us with 1 over x minus 5. Square and the square cancel. You got x plus 3 minus 8. That becomes x minus 5. Now that we've taken care of the composition, we'll look at this function holistically and determine where it is undefined. So we have 1 over x minus 5. We need x minus 5 to not equal 0, which means we need x can't equal 5.
If we were to go backwards and plug that into the square root of, the x plus 3, would it still be the same?
So 5 can be plugged into the square, the square root function, can't it? But it can't be plugged into the composition. So that's gonna play a big, like, I'm gonna clarify that one in just a moment. That's a good thing to notice. So the last step before we finish is to combine steps 1 and 3 to find the domain of our function. From up above in blue, we need x greater than or equal to -3, and we need x to not equal 5. So we can draw a number line for this situation. If it helps, here's -3, here's 5. We have to pluck out 5, and we have to do everything greater than or equal to -3. So we just need to make sure we pluck out that value. So f composed of g of x, we found it to be 1 over x minus 5, and the domain is bracket -3 to positive 5, union 5 to positive infinity. Okay, so let's talk about why these steps have to happen. Why is it that I need to look at the inside function? So why step 1? Oh, do you need a second? Okay.
Is this driving?
Because why do I need, because g of x is driving this situation. If I can't plug it into g, I certainly can't plug whatever, I can't plug it into f. Because I'm going to be trying to do g of undefined, f of undefined, which won't work. So point being, if I look at this function in its simplified form, it looks like the only issue is x equals 5. But why is it that I need to do it? By definition, f composed of g of x equals f of g of x. So at x equals, let's say, -7, we have f composed of g of -7, which would be f of g of -7. Don't worry, once we write it all out, because I know it's a lot of writing, we're going to explain what's going on afterwards. But g of -7 equals the square root of -7 plus 3, which is the square root of -4, which is not a real number. In the context of this course, it does not exist because we only want to work with real numbers. So the point being, I'll let everyone write it down and then we'll explain. So based on the definition, you have to be able to plug it into G in order to put it into the whole composition. But if you try and plug in a negative number that's less than -3, so -7 was my choice. I could have just as easily chosen -4 or -5 or -10 or -2 billion, but I decided on -7. So in order for the composition function to be able to compute that value, it needs to be able to compute g of -7 in the first place, but you can't. It gives us not a real number. That's why step 1 is there. So step 1 says, make sure it can be plugged into the inner function first before you even go further. Because if it can't be plugged into the first function, you can't get a result to plug into the outer function. Let me say that one more time. So the composition function says you need to check whether or not it can be plugged into the inner function, because if it can't, then you can't plug that result into the outer function. So very, very going into it, Connor.
So is it only not a real number because of square root?
Because the square root, yeah. Yes.
Okay, so let's say that under the square root, if we're x minus 3.
Mhm.
how does that change something? Cause I do remember you mentioning something at one point that like. Two negatives or not, yeah, like that there could be a possibility of like, there is a negative that eventually like. Come into a positive.
That can happen, very, very rare. But if it was x minus 3, then this would just be you'd have to have x greater than positive 3. And so this 5 would still play a role. But let's say it was minus 10. Then you need to have x greater than or equal to negative 10. Oh, but then that would also change everything here. So never mind. Never mind. So it depends on each function, I guess is what I'm trying to say, is that every function will result in new possibilities. And so each one, but this procedure works every time. Okay. So let's do another example to kind of bring it home. Given that f of x is equal to 1 over x and g of x is equal to 5 over x minus 3, find g composes f of x and its domain. So g composed with f of x is by definition g of f of x. So to explain it one more time, the reason why we have to do step 1 is that we need to make sure it can be plugged into f first, because if it can't be plugged into f, then we have nothing to plug into g. We have nothing to plug into the outer function. So step 1 is to look at the inner function. F of x is equal to 1 over x. We need x to not equal 0. And I'm going to draw this. I'm going to write this on the side. You don't need to write this. So we need to look like, so step 1 says that we need x to not equal 0. If we were to try and do it by the definition, that would be g of f of 0, but f of 0 is undefined. So g of undefined, what would that be? Nothing. Can't be anything. It's undefined. So that's the first step. Now we will work on the next thing. So we will actually compute it. F of x is 1 over x. So this is g of 1 over x. So we'll write this as, we're going to plug in 1 over x for every instance of x that we see. G is 5 over x. So that'll be 5 over 1 over x minus 3. And once again, you can think about it, g of a box is equal to 1 over the box, 5 over the box minus 3. And we're just plugging in a 1 over x. That's what we're doing. If that helps you, do it. So now we go into step 2. We're going to simplify this function. You can still get there even without that fact, but it's better to just work through it. And so this is going to equal step 2. We're going to simplify it. So it's 5 over 1 over x minus 3. I need a common denominator. So I'll multiply this by x over x. And this will become 5 over 1 minus 3x over x, which is equal to 5x over 1 minus 3x. And even if we looking at the time, I don't know if we'll get to unit 3, and that's okay. I've banked on that, so it's okay that we don't get to it. So from here, Does anybody have any questions on the algebra that happened? It's okay if you do.
Yeah, with five X.
So flip and multiply. That's what's happening because I'm dividing by a fraction. So flip and multiply, that's why it becomes 5x, but the denominator is now 1 minus 3x. And so that was step 2. And then step 3 is to look at the function and define like this new function and find where it is undefined. So step 3, we need one minus 3x to not equal 0, which means that x cannot equal 1/3. So we have 2 conditions. Let's draw a number line to figure this out. Here's 0. Here's 1/3. From the green, we need 0 plucked out. From the orange, we need 1/3 plucked out. But everything else is fair game. So g composed with f of x is equal to 5x over 1 minus 3x, and the domain is parenthesis negative infinity to 0, union 0 to 1/3, union 1/3 to positive infinity. Really? Okay, I'll move this. All right. Ben, yes.
Couldn't. Okay, I understand why we got 1/3.
Mm-hmm.
When I looked at this initially, I just looked at them individually. Without doing any of the math in between to try and like give myself a head start, right?
Uh-huh.
So I got x doesn't equal 0 or 3. That is still also true because that would make 1/3 the 1/3 that we don't need.
Will it become 1/3 minus 3? And that,
Okay,
and
that's
so
the
that-
minus, the 1 minus 3 times 1/3.
yeah, so you need to do 1/3 in it so that you could flip and multiply and make it 3.
Okay.
Yeah.
Gotcha, and we just can't look at these separately though.
I mean, you can a little bit. You can look at it separately. Like, there is nothing stopping you from right here. It's just usually when it comes to composition functions, without simplifying, it becomes very convoluted. And like, depending on how much you simplify, will drastically change things. And so, like, this one was a great example of why, like, you can look at it right here and figure out where the denominator, what the denominator should be, even without simplifying, but it's a little more tricky to do. Whereas this is a nice systematic process. But you can look at it holistically to figure it out, though. Okay. My favorite example in this section, my favorite example, unless there's any other questions on this one. Good? Okay. Say what? Yes. Yes. And let me see. Let me look at something real quick. I want to make sure. Just 2.6. I didn't, yeah, okay. I didn't want to put 1.8. So I think after this problem, I think we'll have enough. We can call it good after this one. We'll save the last one for on Thursday of next week. So this one's really, really cool. The graphs of f and g are given. We don't know what the equations are, but knowing what we know about piecewise functions, we could create the equations. We totally could. But it's saying you're not given those, but you need to find these values. Oh no, we can't compute them because we don't know the equations. Appeal straight to the definition. Exactly right. We'll use the lines. So, in particular, f plus g of 0 is by definition f of 0 plus g of 0. That's what the algebra tells us. And so I'm going to color code this in green. F of 0 equals 4, and G of 0 is equal to 2. So this is equal to 6. So based purely on the definition, that's what it is. That's all you need to do. It looks really intimidating. And those are my favorite types of problems where they look intimidating, but they're actually very, very approachable. G divided by F of 5. That is by definition G of 5 divided by F of 5. So I'll do this one in blue. All right, no, let's use colors that aren't red and blue. Let's do purple.
Isn't the difference just the space between G and F?
The difference would be, yes. The difference would be the difference in the heights of the two. Yes. That's a very, very good way to view it. And this one is just taking the quotient of the two functions. And so G of 5 is 1. And F of 5 is 5. So this is equal to 1/5. And there's so many more we could ask. We could say, what is F minus G of -5? It'd be a little bit difficult because we need to know the align. That'd be a fun challenge problem, actually. I'm going to add that in at the end if you're curious to do one. But anyways, we'll move on to these next ones. G composed with F of -6. Looks more intimidating, but if you remember what the definition of composition is, this is not as scary. So this is by definition G of the quantity F of -6. So what is -6? Oh, let's use orange. What is F of -6? It's the blue curve. F of -6 is 2. So this is equal to G of 2. And G of 2 is -2. A lot of definition chasing. A lot of looking at the graph to find things.
I keep seeing G of X like Joff.
Yeah, like it looks like Joff of X or Goff of X. And this is Gog of X.
How come you use blue line?
The blue line for F. F is the blue line. And so I needed to first compute F of -6. So that would be on the blue line, F of -6 would be the Y value at -6, which is 2. And that's where I get that. And then into it. Bet.
What's the relevancy? Why does this matter?
Critical thinking. That's about it.
It's mathematician being mathematician.
Yes, it's us just having fun, saying, look, isn't it cool? We could do this without even knowing what the functions are.
Because I'm looking at the two graphs like, okay, cool, but still there's no correlation between those whatsoever.
Yes. Now that brings up a very valid point, is that later on, this gets made more clear on what we can do with it. If you like, I remember you mentioning you want to do computer programming, like game coding. And game coding, they do it differently. They write it differently than we do. And it's been driving me nuts as I've been trying to learn how to code, because they don't write it the way a mathematician would, and it's making me mad. But they have their own version of composition. They use a dot instead. So they say in coding, they say your variable, let's call it speed dot get string and then parentheses. That's a composition. In coding, they are using composition. They're just not writing it the same way.
Yeah.
So that is we are looking at it purely abstractly with these weird functions, but this will get once you go into higher division courses that require mathematics, they are using it. So we are getting comfortable with it. So I mean, imagine a very, very good analogy would be learning how to play with Legos so that you know how to make a set, right? I'm showing you how the blocks fit together. And then later on in the next course or in a computer science course, they'll say, here's how you can use the blocks to make a super cool spaceship.
Yeah, and that makes a little more sense later on though too, because there's like definitions for the numbers. Right now, we're just playing with numbers for the sake of fun.
Exactly.
Which is really like you said, it's abstract, it's weird to think about.
But I like to push the bounds of what is uncomfortable in mathematics. So this is g of 0. You're composing the function with itself, and it won't give you back the same number, which is pretty silly. Sometimes it will, but not always. So g of 0, let's use gray. G of 0 would be 2. So this is equal to g of 2. And then let's use brown because we ran out of colors. G of 2 is -2. Fun problem. Connor, you look like you want to ask a question.
My question, yeah. I don't even know how to ask it.
For sure.
Where's the 2 come from?
The gray 2?
Yeah, so like, I don't know, I guess I just looked up and you got G of G times 0 equals 2. That makes no sense.
So you're getting caught up on the parentheses trying to mean multiplication when then all those parentheses do not mean multiplication. They mean function notation. So when you compose it, it's g of this quantity. So g of 0. G of 0, this is not g times 0, this is g of 0. So we're looking for the y value of g when x is 0. When x is 0, the y value of g is 2. So imagine ignoring this for a second. What is g of 0? It's 2. Then, so I'm replacing g of 0 with what it actually is, the value that it is, which is 2. And then I'm now computing g at 2, the y value when x is equal to 2, which is -2. Is that okay?
2-step.
Yes. That's exactly what Hector was saying. Yeah, you're working inside out. You're looking at the thing from the inside out. You're working one step at a time.
How Asians read.
Oh yeah. Like specifically, I don't know about Chinese. I don't know Chinese, but I know Japanese does read right to left. So yeah, it's much very, very similar to that situation.
You got that too from the 0, right?
Yes. Yeah, I'm using the graphs to figure these out.
You just switch up.
Any other questions? Because this is conceptually difficult. Believe me, I love this question, but it is difficult. Once you start to get it, though, it's great. And so if you want a really challenging problem, I might even add this as like an extra credit problem. This is a cool one. Find f composed of g of, let's see here, g, if I do g of no, if I do g of 4, no, okay, I'm trying to find a good one. G of -4. Aha, yes. Find g composed of f of -6. Bonus problem. Like maybe it might show up on the exam. Maybe it might show up on the exam as an extra credit problem. Or maybe it'll be added after the fact for the exam. Like you can find out after, like we can put it on the exam as a little bit of extra credit to boost exam grades.
And like, let's say it's a 5 point, if you get it wrong, you get, let's say.
Yeah, you consider it partial credit.
Yes.
Absolutely. So this one is a nifty little question. And if you want a hint on it, let me know and I will give you the hint. But at least computing what g of -6 is will get you started. And then you'll have to think about lines. That's my hint. Hint. Equations of lines. That's my hint. It might not make any sense right now. Let it marinate, for a good 12 hours to make sure your steak is delicious. Or marinating steak is marinating chicken, right? Marinate a good marinade on some chicken thighs. You know, you gotta wait a day or so to make sure it's really gotten in there. So let yourself get that time. We'll call it good here. If you guys have any questions, feel free to ask. Otherwise, have a great rest of your day. Have a great Halloween. Make sure you don't eat any candy with razor blades in it. I've never had that happen, but you know, don't make sure it's not opened candy. And avoid the social medias, avoid doom scrolling. Happy studying, and I will see you guys on Tuesday for the exam.